This call is now being recorded.
Okay, can you see the screen now?
Yes, sir.
Okay. All right. So yesterday we learned about fracture toughness now. You remember? Yeah?
Yes, sir.
Anyway, before going for fracture toughness, what is this curve? What is this curve that is indicated on your screen here? Yeah? What is this curve called?
Stress strain diagram.
Stress strain diagram. So for
Brittle.
what type,
For
for
ductile.
what type of material it is stress strain diagram?
Ductile.
Ductile, sir.
Okay, ductile. Okay. Who is that? Answered Mithun or Ganush or Sukrut?
Both, sir.
Okay, fine. That's fine. What is this, Ganush here? In yellow
Sir,
color?
elastic region, sir.
No, he has written here, no, modulus of resilience. Okay, whatever. So resilience
Sir.
is what we learned. So in the previous module or in this module previously, we learned that two things in stress strain curve is one is resilience, another is toughness. Correct? Yeah. Yeah. Mithun, what is this part? What is this that is typed here?
Sir, modulus of toughness.
Modulus of toughness. This is modulus of
Resilience.
resilience. Okay. So again, coming to this stress strain diagram, what is indicated here in the pink color here? Sukrut?
Elastic region.
Plastic region. This is blue color?
Elastic region.
Elastic region. So coming back to this stress strain diagram that we have got, this is modulus of toughness. This is resilience. Correct? That is anything beyond the elastic region or the area under the curve. I'll come to that. Okay. The area under the stress strain diagram beyond the elastic region is called toughness. Is that okay? Are you there?
Yes, sir.
Okay. So the area in the stress strain diagram, the area after elastic limit up to fracture is called the toughness. All right. So then what is fracture toughness? So to understand what is fracture toughness, that means so it can take up this much strain before failure. That is the meaning of toughness. That is, if the material is very tough, that means its yielding is larger. So therefore, aluminum has got better toughness than a cast iron because cast iron breaks. Here it says there is no yielding, so it is strong, but it is not tough. But aluminum is tough because it has got more strain absorbing power. Is that okay? That is the area under the stress strain curve of an aluminum is large. So therefore, its toughness is also more. Okay. So what is the region for toughness? Mo please tell me the region under the toughness is the region under plasticity. Okay. So the area under in stress strain curve in plastic region represents toughness. If this area is more, okay, then its toughness is more. Could you all understand what I mean to say?
Yes, sir.
Okay, toughness you understood. Now let me come to fracture toughness. So what is fracture toughness? It is essentially the toughness of the material when there is presence of a crack in the material. That is fracture toughness. Could you get the clarity of what is fracture toughness now? Are you there?
Yes, sir.
Yeah. So now, yesterday I think we saw this slide. Anyway, let me go back again because I think fracture toughness we did not understand yesterday properly. Okay, anyway, the fracture toughness is the critical stress intensity factor of a sharp crack where propagation of the crack suddenly becomes rapid and okay. It is essentially the critical stress intensity factor K of a sharp crack. So you understand what is fracture toughness is? The area under in stress strain curve B in plastic region is toughness. Fracture toughness is the toughness when there is presence of crack in the material. That's it. So essentially fracture toughness is the critical intensity factor, stress intensity factor of a sharp crack. One second, I think somebody is trying to join. Okay. All right. So where sharp crack, where propagation of the crack suddenly becomes rapid and unlimited, and the crack will grow in an unstable manner. Okay. And also, what is the application or use of fracture toughness is that it will give you a quantitative way of expressing materials resistance to crack propagation. So more is the fracture toughness, more is the materials resistance to crack propagation. Then better is the components working. So that is the importance of fracture toughness. Then what does this critical stress intensity factor represents? It represents, okay, the for a given load, crack length and geometry required to cause yielding. Okay, that is essentially for crack length and geometry to require fracture to cause fracture. Okay, it is the stress intensity factor K for a given load, crack length and geometry required to cause fracture. So whenever the fracture is occurring, then the stress intensity factor is called the critical stress intensity factor. Okay. So next we'll move on to next. So the critical stress intensity factor can be used to obtain critical crack sizes for fracture under cyclic loading. That is one meaning. Next, the general relationship between fracture toughness and thickness is as shown. Actually, the curve should have been coming like this and below. Okay. So what you do is, please note down this sketch. This is fracture toughness, Kc. This is thickness. So the smaller, that is thin plate will be on top. So come down and then come down for the thicker member will be somewhere here. So please note down this sketch in your notebook. This is thin section, this is medium, and this is thick member. This is plane stress, this is a plane strain, this is mixed mode. Okay, and you have to draw the slope compulsorily. Without the slope, it is not correct. Higher slope, lesser slope, and no slope here. Please write this diagram in your notebook. This is fracture toughness in y-axis, thickness in x-axis. This should be at the top. Below that is medium. Below that is thick. This should have been more steeper like this. Finished, huh? Finished writing? Is it over?
Yes, sir.
Finished, huh? So please observe
sir.
that.
Yes,
This is a
sir.
this is a thin plate. Thin plates are subjected to plane stress. Then this is the medium plate. There's a steep here, lesser steep, which is a mixed mode. And this is the thick plates normally are subjected to plane strain rather than plane stress, because plane is the one which has got length and breadth but negligible thickness, whereas thick plate are subjected to not plane stress but they are subjected to plane strain. Okay, now let's understand the importance of this fracture toughness, or what is the fracture toughness and what are the features of fracture toughness over there. Okay, the beach markings at the initial crack tip represent fatigue. Okay, and then fracture toughness is the energy absorbed by the material with the presence of crack. Again, this is what I was telling. Stress strain diagram, when you look back, stress strain diagram. Okay, so the area right in plastic region is called toughness. If there's the presence of crack, then it is called fracture toughness. Again, it is the energy absorbed by the material with the presence of crack is called fracture toughness. Yeah. Again, from the figure, coming back to stress intensity factor over here, it can be seen the thin parts have high critical stress intensity factor. Okay, that is, they have got high stress intensity factor, Kc, compared to this one. This should have been somewhere here. Okay, so anyway, so the thick parts have got low stress intensity factors. Okay, that is here. Okay, and the thin parts have got high critical stress intensity factor. You understand? That's the one thing. And then accompanied by appreciable shear lips or slant fracture. So this type of fracture is a high energy fracture. Next, as the thickness is increased, percentage of shear lips or slant fracture decreases, as does intensity factor, that is critical stress intensity factor. Okay, this type is called mixed mode. Then in thick parts, the entire fracture surface is flat. This is very, very important. And then any further increase in thickness does not decrease the fracture toughness, nor does it alter the fracture surface appearance. So please remember, so if it is thick surface, it's going to be on a flat, it's going to be a flat surface. If it is thin, it's going to plane stress, and the shear that is present, and it's a high energy fracture, and it is accompanied by appreciable shear lips or slant fractures. This is the behavior of or the importance or features of critical stress intensity factor for thin, medium, and thick materials. Next. Next, we learn about fracture toughness can be very sensitive to metallurgical conditions. That is, grain orientation, chemistry, then microstructure. Okay. So by having uniform grain orientation, we can enhance the fracture toughness. Then by having proper heat treatment, we can enhance fracture toughness, and then we can have microstructure, which is devoid of any inclusions and voids. We can enhance the fracture toughness. So by varying these variables, that is grain orientation, chemistry, and microstructure. By systematically controlling these three parameters, we can enhance the fracture toughness. That is essentially resistance of materials for crack propagation. You all there? Are you all there? So it is essentially
Yes.
a system of material for crack propagation. This can be enhanced by having or systematically controlling grain orientation, chemistry, and microstructure. Now please note down this much. From fracture toughness, and also you write this. This is very important. Low impurity. That's what I said. In microstructure, you should not have any voids, inclusions, and so on. So low impurity materials can provide better fracture toughness. The same thing over here. So better you write fracture toughness to up to this. Note down in your notebook. Finished, huh?
No, sir. Yes, sir.
Okay. Next. The fracture toughness can also be influenced by effects of crack tip geometry. Okay, so this is also another factor, that is crack tip geometry, which will influence fracture toughness. That is, if it is blunting, irregular crack front, then it's going to be haphazard movement of crack, a change in the mode of crack extension, and branching. That is, it can go in different directions like this. Crack can grow in different directions, right? So these things can influence the fracture toughness of a material. Okay, so please note down this also. Fracture toughness can be influenced by the effects of crack tip geometry such as blunting, irregular crack front, change in mode of crack extension, then branching. All right. So again, the fracture toughness again depends upon temperature, strain rate, corrosive environment. Please note down these three also. So in total, there are so many factors that will influence fracture toughness of metals. Note down, the fracture toughness also depends on temperature, strain rate, and corrosive environment. Okay, finished? Note it down.
Yes.
Okay, so again, so what finally are the factors that influence fracture toughness are grain orientation, chemistry, microstructure. So by controlling these parameters, we can systematically enhance the fracture toughness property of a material. Then it is also influenced by the crack tip geometry, such as blunting of crack, irregular crack front, and then mode of crack extension and branching of cracks. So these are the factors that will influence fracture toughness. Also, the temperature, strain rate, and corrosive environment. These three also in total influence fracture toughness. So totally these three, these four, and the other three, grain orientation, chemistry, and microstructure, these are all the factors that will influence fracture toughness. Okay. So fracture toughness is resistance of material against crack propagation, and it is given by area in plastic region. Okay, area in the plastic region when there is a presence of crack is called fracture toughness. All right, could you get the clarity now? So for once you think of fracture toughness, you think of stress strain diagram. In stress strain diagram, you think of elastic region and plastic region. The plastic region is called the modulus of toughness. So in the presence of a crack, that modulus of toughness becomes fracture toughness. All right. So this fracture toughness, okay, is the energy absorbed by the material in the presence of crack. All right. Then we have got fracture toughness being influenced by grain orientation, chemistry, microstructure, blunting of crack tip, then irregular crack front, branching of crack, and then mode of crack extension, and temperature, strain rate, and corrosive environment. So this is about fracture toughness. Then the path of crack during fracture is usually controlled by microstructure, the dominant constituents being precipitates, grain size, texturing due to mechanical working, right? So the path of crack during fracture is this is controlled by microstructure of the material. So that is why in material science, the study of microstructure is a very important parameter, because that will give you an idea as to how the crack will propagate, or the path of crack during fracture. Fracture is determined or controlled by such microstructure. So the dominant constituents in microstructures can be precipitates. Say suppose if they do mixing, no, various metals like metal matrix composites and all, there will be inclusions. So there should not be any precipitates present in the microstructure. That's why in all material science they take microstructure photographs to look for such precipitates. If there is any presence of precipitates, then path of crack during fracture is influenced by the presence of such precipitate. They are like essentially inclusions. So this is what we have been studying for past two modules. That presence of voids, inclusions will lead to crack propagation or crack nucleation and crack propagation. Right now, so precipitates is one of the types of inclusions where the cracks can nucleate and propagate. Then second one is the grain size. Okay. So if you have uniform grain size, then material will have greater toughness. That's why to improve the grain size, what operation they do normally to improve the uniform grain size or to obtain uniform grain size, they do one operation or process. What is that process called? What is that process? It is heat treatment. So by heat treating the components, one can get uniform grain size. Why we need to have uniform grain size? This is the reason, because that will control the path of crack during fracture. Is that okay? Could you understand what we are dealing with? Okay. Then is texturing due to mechanical working. So what type of texture that you are going to get while doing grinding, milling, or turning operations? Then what is the influence of fracture toughness on allowable stress or crack size is the next question. Right now, so influence of fracture toughness on crack size is the next topic. So before that, you note down this sketch. This is stress in y direction, crack length in x direction. Then stress is given by KIC by root pi into A. KS is critical stress intensity factor. So this is what we learned here. So here we have got critical stress intensity factor KIC. I represents mode of fracture, that is mode 1. Okay. This I stands for mode 1, that is essentially mode 1 is subjected to tensile loading. Okay, that's it. Please note down this sketch completely. This is lower KIC. This is stress. This is crack length. As stress increases, crack length decreases. I mean crack length in meters. Finished taking a diagram? All right. Okay. So this is the equation, that is stress is equal to critical stress intensity factor in mode 1. This I stands for mode 1 type, that is mode 1, 2, 3 we learned in the beginning of fracture mechanics. So KIC represents critical stress intensity factor in mode 1 divided by root pi into A, where A is crack length in meters or millimeters, whatever the unit. Next, the allowable stress in the presence of crack size is directly proportional to fracture toughness. This is what is. So, thus increasing the critical stress intensity factor has a much larger influence on allowable crack size than on allowable stress. So, as the KIC is more and more, okay. So this is higher KIC, which has got more and more influence on stress. And then, okay, so the region above the curve is curve identifies the fracture region for monotonic loading condition. So therefore, again, limitation of LEFM, it is that the stress induced should be less than the yield strength by 80%. So that is what you have got 0.8 SY here, right now. So one of the limitations that we learned in previous classes was that in LEFM, the strength, that is the stress induced, should be less than the yield strength. Okay, so that is what again is reiterated here. That is, it should not exceed 80% of yield strength. Next is fatigue crack growth dA by dN delta K. Okay, so before that I'll sum it up about fracture toughness that we learned. Okay, so from stress strain diagram we know this is the modulus of toughness. Okay, so this is, if there is no crack, this zone in plastic region is called toughness. More the area, that is the area under the stress strain curve in plastic region is called toughness. More the area, more is the toughness. So ductile materials will have better toughness than brittle materials. If there is a presence of crack, okay, in the metal, then this area is the area under the stress strain curve in plastic region is called fracture toughness. Okay, and essentially critical stress value of the intensity factor is called critical stress intensity factor Kc, which is given by the equation that we have taken yesterday. Again, fracture toughness is the critical stress intensity factor K for a sharp crack where propagation of the crack is becomes suddenly rapid and unlimited or uncontrolled. Okay, and fracture toughness is a quantitative way of expressing material's resistance to crack propagation. So more is the toughness, fracture toughness, more is the material's resistance to crack propagation. That is what is required. Then we learnt about influence of thickness, okay, on with reference to fracture toughness. In that, we learned that so the energy in the thin sheets or thin parts, we have high stress intensity or critical stress intensity factor, okay, whereas in the thick parts, the entire fracture surface is flat, and the any further increase in thickness, that will give you the limitation, does not decrease the fracture toughness. Okay, and then we learnt about what are the factors that influence fracture toughness. Essentially grain orientation, chemistry, microstructure, temperature, strain rate, corrosive environment. Then when it comes to crack tip geometry, it is blunting, branching, irregular crack front, and mode of crack propagation. Okay, and also in the path of crack, okay, that is nucleation and propagation of crack, is controlled by these three parameters. One is precipitate, grain size, and texturing due to mechanical working. So these are all the things that we learnt in fracture mechanics. Okay, then we are going to go for fatigue crack growth. Okay, fatigue crack growth. So the strength of component or structure can be significantly reduced by presence of a crack or discontinuity. So this is universally we have been learning right from module 1 when we started with fatigue, where the strength of the component will definitely gets reduced, okay, because of the presence of crack or discontinuity. So the discontinuities can be presence of a notch, hole, fillet, stepper shaft, and so on, okay, or voids, inclusions. So these things can be called as discontinuities. So in the presence of such discontinuities, the strength of the component would definitely, component or structure will definitely gets reduced. Okay. So commonly subcritical crack growth occurs from existing crack or discontinuity until a crack size is reached, causing fracture. Okay, this again same as above. So common type of subcritical crack growth is due to fatigue in the presence of an existing discontinuity or a crack. So this we have been learning for a long time now. Okay, so that is what is a linear elastic fracture mechanics, where we assume the presence of a crack. So subcritical crack growth is due to essentially fatigue or repeated loading cycles. So that's where the subcritical crack growth will occur. Next, what you do is you note down this sketch. In y-axis, y-axis you have crack length, and in x-axis you have got number of cycles or applied cycles. Okay, so please note down S1 greater than S2 greater than S3. This is very, very important. Stress 1, so higher stress, this greater than S2, again greater than S3. So S1 is the greatest stress. Okay, so therefore the applied number of cycles will come down. If the stress is less, so it can go for more number of cycles. So that is what it all means. So crack length versus applied cycles, right now. So where it is subject, the specimen is subjected to different repeated stress levels. Okay, one may be subjected to 300 megapascal, the second one may be 200, and third one may be 100 megapascal. That is what is indicated in S1 greater than S2 greater than S3. So then again, condition is that all specimens contain the same crack length A naught, and in each test, minimum stress was 0. Okay, so we can see that higher the stresses, the crack growth rates are higher at a given crack length and fatigue crack growth line. That is total number of applied cycles is short. That is naturally, this is what we have been learning. Even in basic SN diagram also, higher the stress, lower is the number of cycles that it can withstand. Same thing over here. Okay, how the crack for crack growth also uses the same analogy. Subject the component of same crack length. Okay, all the three have got same initial crack length. If you see, this is A naught. That is the original crack length. But one is subjected to higher stress values, that is S1. It will have number of cycles being reduced over here. For same crack length, reduce the stress value. So maybe S1 is subjected to 300, S2 may be 200, and S3 may be 100 megapascal. So as the stress is lesser and lesser, the number of cycles that it can withstand before fracture is more and more. Okay, for the same initial crack lengths. So that means if you don't want the crack to propagate, you should apply less stress on the components. Are you there? Could you get the clarity with this? Yeah. Please note down the
Yes, sir.
sketch. Finished, huh? Finished?
Yes, sir.
Can someone volunteer to explain this again? Just comprehend what we learned here. Dhanush, Mithun, can you just comprehend what we learned here in this slide? Sukrut, Sandesh, yeah? Can anyone just tell whatever that you have learned from this? Let's see. Okay. Mithun, start. Or Dhanush, can you?
Sir, as the with higher stresses, the crack growth rates are higher at a given crack length and fatigue crack growth life, sir.
Okay, okay. That is, take three specimens, have same crack length, subject each of them to different stresses. That is, S1 is greater, S2 is lesser, S3 is much lesser. So, with the initial crack length being same for all the three specimens, the specimen with higher stress will have lesser fatigue life. Okay, and the specimen with lesser stress, subjected to lesser stress, will have more number of cycles of life. That's all. Is that okay? Could others understand what it is?
Yes,
Okay, right. So that's what, and then that is for here it is given for initial crack size, the life to fracture depends on magnitude of applied stress and the fracture resistance of the material. That is, it is essentially life to fracture, that is fracture life or the life of the component depends on magnitude of applied stress. So here S1 is the higher magnitude stress. So therefore the life of the component comes down or its fracture life is lesser compared to a component which is subjected to lesser magnitude of stress. That's all it means. Just note down this sentence. Just note down this sentence. For the given initial crack size, the life to fracture depends on magnitude of applied stress and fracture resistance of the material. Please note down that sentence only, which is in italics. The entire diagram that you have taken can be concise to this sentence. Can be told in this. So same initial crack size. So for the component to fail, it depends upon magnitude of applied stress and fracture resistance of the material. That's all. It depends on applied stress and resistance of material. Finished, huh? Noted down? Finished?
Yes, sir.
Okay. So what we learned is about fracture fatigue crack growth. Before that, fracture toughness. Then fractures influence of fracture toughness on crack size. Then we learned about fatigue crack growth a bit, and then we understood that for initial same crack length, so material which is subjected to lesser magnitude of stress will last for longer duration in service. Okay, This is what we learned. Okay. Again, Monday. Yeah. For 4 of you, I sent PPTs. Did you receive?
Yes, sir.
All the 4
Yes.
got it?